Alright folks, so in the question that we have here, we can see that we have an elevation here, plan view of it here, and we have a pictorial view of the structure given to us down here. Now when we start off with a question like this, obviously starting off you'd read the question and then straight away you go into labeling the actual object, because what we want to do in this question is complete a surface development of it. So it says, question 2, the projections of a sheet metal duct transition piece are given. Complete a one-piece surface development of the transition piece. So we can see from this structure here that it is sloping upwards, and the actual square bit here, what you might appear to be at the top, it's actually on the base, and then the rectangular bit on the outside is actually at the top. So it's sloping upwards. So this bit in here is actually on the ground, whereas this bit on the outside is above the ground, a certain height from there to there, based on the XY line. Now, first thing we would always start off with is labels. Okay, so if I was to label this, I'm going to start off with the top bit, and I'm going to label each corner 1, 2, 3, 4, and I'm going to label the square on the inside. I'm going to call this one 5, 6, 7 and 8. They are all our definitive points, because 1 joins to 2, 2 to 3, 3 to 4, 4 back to 1, 5 to 6, 6 to 7, so all the way around, and then 1 joins to 5 and 6, 2 joins to 6 and 7, 3, 7 and 8, 4, 8 and 5 back to 1 obviously. And what we're going to use is those labels. Obviously if we label them in plan, we're going to label them in elevation. So 1 and 2 are going to be up here, got 3 and 4 over here. We have on the outside 6 here, and 5 is at the back, 7 is at the front, and then we have 8. Okay, now straight away looking at this, and as we've seen in other questions, if we look at the base of it, 5, 6, 7 and 8, well 5, 6, 7 and 8 are all on the ground, so therefore we can take 5 to 6, 6 to 7, 7 to 8 and 8 back to 5, they're all true lengths. And then also 1, 2, 3 and 4, we can see that they were up here. Let's pull that down a little bit there. 1, 2, 3 and 4 we're up here, so we can see that they are parallel with the XY line, therefore they are all also true lengths. So 1 to 2 true length, 2 to 3, 3 to 4, 4 to 1, and we can see 1 and 2 is the same as 3 and 4, or 2 and 3 is the same as 4 and 1, and so on. Now what we don't have true lengths for is the lines 1 to 6, 1 to 5, 6 to 2, 7 to 2, and all these lines in here connecting them. And the reason they are not true lengths at this moment in time is because in the lines down here, all these lines that I just named there, none of them are parallel to the XY line in plan, and none of them are parallel to the XY line in elevation. So what we need to do is we need to use Cohen's analogies, or the principle of Cohen's, to get true lengths. And looking at this straight away, I can see just symmetry. I can see 1 to 5 is the same distance as 2 and 7. So when I find the true length of 1 and 5, I can use the same for 2 and 7. 1 and 6 is the same as 6 and 2. So that will take care of this side. 5 and 4, 5 to 4 is the same as 7 to 3, and then 3 to 8 is the same as 8 to 4. And what we can do is just use those. So we need to find the true length of a couple of these here. And the way of doing that, we've explained previously, is literally just using Cohen's as a principle. So if I take 1, in this case, as the apex of a cone, okay, if I take 1 as the apex of a cone, and then to find 5 and to find 6, it's literally a case of rotating them until they're parallel with the XY line. So from 1, I'm going to do a straight line out, and I'm going to rotate the radius, because in plan view of a cone you'll always see a circle. So at 5, I'm going to rotate that around to there, and I'm going to do the same for 6. And now when I'm looking at them, 6 is coming to this position here, 5 is now here. It's literally a case of I'm going to project them up to my XY line, up to my elevation, here and there. Okay, so I've now found a new position. 6 is inside in here, and 5 is this guy. and they are both going to join up to number 1. And what I have there now is actually 2 lines. And the inside line, so I'm just going to write inside here for the inside line, and I'm going to write out here for the outside line. So for the inside line, that is the true length of my line from 1 to 6. So for the inside line, just put a little arrow there. That is my true length for 1 to 6. And as I said, 1 and 6 is the same as 6 and 2. So I'm going to say 2 to 6 as well. And then the outside line is my true length for 1 to 5. So I'll put that in there. So recognizing 1 to 5 is the same as 2 to 7. Okay, so that's that much done. Because the reason for that is because, once again, 1 here, and now 5 was in this position, and 6 was here and 5 was here. They are now parallel with the XY line, which means that they have to be true lengths in my elevation. Now, that's worked out basically everything. I have 1 to 5, and I've got 1 to 6 as a true length. I've got 6 to 2 and 7 to 2. So that's worked out everything on this portion of it here. Now it's a case of working out what's on this side. Okay, so I'm going to in this case, I'm going to use 4 as my apex of a cone. And what I'm going to do is from 4, I'm going to drag a line out parallel with the XY line, and using the exact same principle again, start with 4 and 8. 8 is in here. Rotate that around, and the same with 5. So we can see there's a little bit more of a difference in this case. This time we're to hit the extreme generator, because the extreme generator is coming out here. The extreme generator is always going to be parallel with your XY line in this case. So labeling again, in this case we had 5 on the outside once again, and this was 8. Okay, join them up to my 4, because that is the extreme generator of a cone as we would see it. There we go. And once again, inside here I'm going to label the true lengths. So this one here is the true length from 4 to 8, which is the same as the true length from 3 to 8. And this guy on the outside is a true length from, just make sure I have him, yeah, 4 to 5, and which would be the same as 3 to 7. So now in that case, I have 8 lines if we work it out. 1, 2, 3, 4, 5, 6, 7, 8. And with all of those, if I have true lengths for 8 of them, 1, 2, 3, 4, 5, 6, 7, 8. Therefore, we are ready to complete the surface developments now, because we have every true length of all the lines down here to actually make up the object. Okay. Now, in completing the surface development, I'm going to start with point number 1. And what we're going to do is, you can see here we have a series of triangles in completing our structure. Okay, now obviously the bottom is left open, the top is left open, so it's just the outside parts that we have to do. So it's all these 8 triangles here, 1, 2, 3, 4, 5, 6, 7, 8. And we're starting off with the triangle number 1, 2, 6. In this case, as I've indexed it. If you've indexed it differently, that is absolutely fine. So, starting off with 1, 2, 6. So what I'm going to do is I pick a point 1 roughly out here, and I'm going to take the true length from 1 to 2. And at point 1, I'm going to step it off, and that there would be my number 2. Now, at this point, I need the true length of 1 to 6 and 2 to 6. And we can see here that I actually had that up here, and it was the exact same. So, I'm going to take that distance on my compass. It was the inside one now, just so everyone can see there. That one there, 1 to 6 and 2 to 6. And from 2, I'm going to step it off, and somewhere along there should be 6. And the exact same with 1. And where the 2 arcs cross each other, that is my point 6. So there we go. Both of them now can join to 1 and 2. And we're just going to keep continuing on in that sequence until we have the question done. Now, next triangle. If I tick off the triangles as I go up, so that's the first one done, so I know I'm done. Now I'm on to 2, 6, 7. And we can see we already have 2, we already have 6, so we just need to find 6 to 7 and 2 to 7. And 6 to 7, I can take that straight as a true length from the sheet. As I explained previously, it is a true length as we looked on top of the plan. So from 6, somewhere along there is 7. And now I need the true length from 2 to 7. And if I come up here to my elevation, I can see that my 2 to 7 true length is right here. And there we go. And from 2, swing an arc. And where the 2 arcs cross each other, that is my 7. And obviously both of them join, or 7 joins to 6, and 7 joins to 2. So there we go. That's 2 of the triangles done. Now I've got this one done. And what I'll do is I'll explain one further, and then I'm going to skip on ahead, because at that point it's just a case of repeating the sequence using the true lengths that we have found up here. So I have the line 2 to 7 done. So now I need the line from 2 to 3. So take the distance from 2 to 3 as a true length. Got it there. And on 2, I'm going to find it down here. Somewhere along there is going to be 3. And now I need the true length from 7 to 3. And 7 to 3 happen to be over here actually. So here we go. So 7 to 3, make sure I just take the right one. That's the true length for 7 to 3, right there. So on 7, put my compass, where they are cross each other, that is 3. They both join up. Okay, at this point now I'm just going to speed it up to complete the rest of the problem. Okay, and as we can see there, that is the full question completed, the full true surface development of it when this structure here has been folded out. And all it actually came down to was just obtaining the correct true lengths and determining which ones we needed at which points. It's just a case of indexing properly the elevation and the plan, and then I use the cones principle with 1 as the apex of a cone up here to find the true length from 1 to 5 and 1 to 6, which is the same as the true length from 2 to 6 and 2 to 7, and vice versa over here. Okay, I hope you found that question helpful. That's complete there.